tools required to terminate the SWA cable is first a pencil, tape measure, junior hacksaw, knife, water pump pliers or grips, and assorted spanners. When installing SWA cable, the gland shroud is the first thing to be fitted to our SWA. Using the SWA as a guide, place the shroud onto the cable so a clear indentation can be seen. Then, using a knife, as demonstrated here, the installer is using a safety retractable knife, we can cut the tip of the shroud removing this and then fitting the shroud onto the outer sheath of the SWA. At a sufficient length down the SWA to provide enough termination at any distribution point or accessory, use a junior hacksaw to cut through the outer sheath and partially cut through the inner armourings. A junior hacksaw is used for this size of SWA. Larger sizes may require the full size hacksaw to achieve this same operation. Once the cut is made, we can use the safety knife to remove the outer PVC covering or outer PVC sheath as shown. Then the armourings can be bent back and snapped off because of where they've been partially cut through, leaving the inner core exposed. The SWA cable gland, part of it can now be fitted to the SWA itself, and we can now remove a small section of the outer sheath as shown by the installer here, which shows the actual makeup of the SWA. Here we see the outer sheath, the armourings and the inner sheath. By taking the inner sheath and rotating around, we can spiral to give a cone shape on the inner armourings. This will help fit in the gland later. Now we need to remove the inner sheath. Carefully score the inner sheath using our safety knife. Be careful not to go too far through so as to damage the inner cores. Next, score down the edge. Again, be careful only to use tiny pressure so as not to damage the inner cores. Peel back the edge and then use the inner cores to tear away the inner sheath. This should tear along our score points to leave a neat termination. The inner cores are twisted together. Untwist these and straighten. The remaining parts of the gland are the gland body, the earth ring and the lock nut. These are to be fitted into the distribution board at the 20mm knockout. Place the gland body in, then the earth ring and then the lock nut. Secure the gland finger tight as shown, and then place the earth ring in position and hold in position by bolting it through the pre-drilled hole. Tighten the lock nut now and the gland together to ensure a good solid connection, a good earth connection to the body of the distribution board. In some cases this will mean removing some of the paint to ensure a good connection. The CPC travels from the earth bar along this cable, which we now can connect to the earth ring at our bolt point. Place the CPC link onto the bolt and tighten the nut to ensure a good electrical and mechanical connection. Tug the earth to see that it is sound. The circuit is to be fed off a 20 amp breaker to feed this isolator. Here we see one end of the SWA as being connected already, and now we need to connect in the end that we have terminated or made off so far. Here is our arm rings that we spiraled. They will go onto the outer edge of the gland. Place the inner course through the centre of the gland. Place the inner sheathing through the centre, but the arm rings must go onto the outside as shown. Then the back nut of the gland can be positioned and threaded onto the outer gland. This can then be tightened by using a spanner. Care must be taken to ensure that no parts of the arm rings come out from the gland at this particular point. When we're happy with the gland connection, we can fit our shroud. The arm ring is connected from both ends now to our isolator, but we need to secure this by means of cleats that will be seen later. A bending machine, tape measure, pencil, square, junior hacksaw, hacksaw, cutting compound, stock and dies, reamer, cloths, bush spanner, spirit level. A measurement is made from the coupling to where the back of the 90-degree bend is to be formed. The piece of conduit is placed in the bending machine with the coupling at the back of the former. The mark that we made is then lined up using the square with the edge of the former at 90 degrees to it. Once this is set up, the bending arm can be forced down over the conduit, wrapping it around the former to form a 90-degree bend. When the bend is close to 90, it needs to be checked for minor pressure to form the exact 90. When this is done, the conduit can be removed from the former as shown. One end of this particular piece of conduit is already threaded, the other end is not. This end needs to be threaded now by using the pipe vise on the bending machine. Secure the actual conduit in the pipe vise as shown. Place compound or smear compound on the part to be threaded. This enables or eases the cutting process. This is the stock and dies, set up at 20mm settings or 20mm die. Turn in a clockwise motion to start the threads. When the threads are started, turn forwards to cut the thread and backwards to remove the cut thread or swarf. Repeat this until the conduit appears through the stock and dies. Allow approximately 2 or 3 threads to ensure that we've cut enough thread for the new coupler. Here we can see that the conduit is starting to appear. When we have sufficient length, we can then remove the stock and dies by reversing the process as shown in the video. Here we see the 20mm cut threads. Using the rags, we can remove the excess compound. By using a reamer, we can remove any internal burrs that could damage future cables. The conduit can now be positioned into our installation using the same techniques as demonstrated on the PVC conduit installations video. Notice the conduit at the distribution board has what is termed a set, a slight bend or double bend in the conduit. This technique will later be shown on a future video. The fixing saddles must be made to secure the conduit to the actual installation wall. This type of saddle is a distance saddle. It ensures that the conduit is spaced off the wall a set distance. The bush can now be inserted into the coupling at the distribution point. This can be tightened by using a special spanner as shown that is termed a bush spanner. Ensuring a tight connection of all couplings and bushes ensures a good earth path, and the metal conduit can be used as a CPC. Once the conduit is installed, we can wire it as earlier shown by connecting now to the 60 amp breaker, and the line of neutral enters the conduit and is connected to the fuse spur. The CPC is connected to the terminal of the accessory, which, because of the metal conduit, we use the metal conduit as a CPC, which is coupled to the metal casing of the distribution board which is connected to the earth terminal here. A pencil, a tape measure, junior hacksaw and 20mm bending spring are the tools required for this installation. The conduit will be installed from the first two-way to the intermediate to the final two-way, and from the first two-way to the light incorporating a 90-degree bend. To install a length of conduit, we need to allow for the two female couplings between the two accessories here as shown, so that we can measure the distance between these two couplers to their internal stop positions. This measurement can then be transferred to a measurement on our length of 20mm PVC conduit, as shown here. This can now be cut to the desired length, as shown. The rough edges can be removed by hand, or if this proves to be difficult, we can use a reaming tool as shown in the video. We can now install the conduit between our two accessories. Having removed one coupling and fitted it to the end of the piece of conduit, we can now insert it into the other, and then using a 20mm bush we can tighten the coupling to the accessory as shown. We now need to form the 90-degree bend. Place the bending spring into the conduit to the point of bending. Note this has been predetermined by attaching a wire to the spring, and the conduit is now warmed by friction at the bending point to help the bending process. The wire allows the bending spring to reach the bending point. This is held onto by the installer so that no kinks appear in the conduit due to the possibility of the spring's incorrect positioning. The installer overbends the conduit to approximately 180 degrees to get a 90-degree bend. Notice that the conduit try to actually return to the original position, hence the reason for overbending. This can now be placed in the installation and marked for cutting to the correct length. Notice the measurement is made to the internal stop points of the couplings. Once it is cut to the correct length, it can be installed as shown, levelled, and marked for conduit saddle fixings by marking either side of the conduit. This is a spacer bar saddle. Notice the two lines from the edges of the conduits that were marked earlier. By fixing to the middle of these, it will be the middle of the conduit. The type of saddle here shown allows for minor adjustments to be made, should that be necessary. The conduit can now be refitted and finally fixed into place with the saddle after final checking by a spirit level, and glued into the coupling points if required. The circuit can now be wired. We need a line from the 6 amp breaker, a neutral from the neutral bar, a CPC from the CPC or earth terminal. The line is wired to the last two-way switch through the conduit. Then it returns via the strappers L1 and L2 to the intermediate, through the intermediate to the first two-way switch, and then via the common link in the two-way switch to the light. Here we see a draw wire that is in the conduit that goes to the light, and we tape these three connections, the line, the neutral and the CPC, to the draw wire. By taping tightly to the draw wire, it ensures that the cables cannot pull off when being pulled from the point of drawing, which in this case is the light, as shown. This is important, particularly on longer conduit runs. All cables should be drawn in together to ensure that no damage occurs to the insulation when drawing cable over the top of cable. The draw wire can now be removed, and we can now connect up all the accessories. Here we now see that the feed comes into the one point, then via the strappers it goes to the intermediate, and then from the intermediate it's connected to the first two-way, and the first two-way from the common connection it goes all the way to the L position of the lamp holder. As we can see here, this is an A3 radial that we previously constructed with 4 sockets, fed from the distribution board off a 20 amp radial circuit breaker. By taking another 2.5 1.5 CPC back to the board from the last socket to here, we can transform this circuit into an A1 ring circuit by connecting into here, here and here, and changing the breaker to a 32 amp. Here we see that the circuit has been installed, the circuit wiring with the addition, and now we have to connect the neutrals into here, the lines into here, and the CPC into the CPC terminal here. When the termination is tight, we can make sure that the cables have been securely connected, and then ease the socket back, ensuring that no damage occurs to the cables. So the cable now returns back to the distribution board to form the ring circuit. Here we see that we have two lines connected to the 32 amp breaker now, two neutrals connected to the same point, and here we will connect in the two CPCs. This is the main earthing bar. This is where they'll be connected. We see that it's in terminal 1, exactly the same as terminal 1 on the neutrals, and exactly the same as circuit breaker 1 on the board. And again we tug to make sure that they are securely fixed. The socket front can now be secured back. Care must be taken when screwing the socket cover back to ensure that no inner cores of the 2.5 twin and earth cables are trapped. To carry out any particular task on a live board, we need to ensure that it's safely isolated. This means that we are required to turn off all breakers, including the main switch. To ensure that no one can re-establish the main switch, we need to make sure that it can be locked off. Here we use a lock-off device that enables us to place a padlock through it, as shown. After fitting the padlock, a warning label must also be fitted stating that no one should turn it on. We then take the key and place it in our pocket. The equipment we need is an approved voltage indicator to GS38. Its leads need to be checked for no cracks or splits, as does the casing. It must have finger guards to stop our fingers slipping into terminations. And the probes must be retractable, as shown, or a maximum of 4 mm. We need to prove that the instrument works by a proving unit, as shown. Once it's proved that the instrument works, we can then test. First we test between line and neutral, then between neutral and the CPC, and then between line and CPC. Finally, we reprove the instrument to prove that it was working as shown. Now it is safe to work. This test is carried out with the circuit dead or isolated. As this is an initial verification, no power will be on. But if it was an existing installation with power on, then this would have to be safely isolated. Please see the previous video on safe isolation. From the loop, the line goes to L1 of our first two-way switch. Then via the strappers that are marked by the sleeving here, it goes through the 3-core and earth cable to the second two-way switch. Then the common connects the strappers to the second switch. Here it returns to the first switch, and when it goes through this to the strappers, returns back on L2 as a switch wire. Testing a lighting circuit involving two-way and intermediate switching can be complex. First, we need to remove the line and the CPC to ensure that no parallel paths can exist and give a false or inaccurate reading. A link is made between the two as shown in the video. Then at the furthest point, a connection is made between the line and the CPC as shown, and a reading is made. By switching at all points within the installation on this circuit, polarity is proved. The reading of 1.06 ohms is recorded as the R1, R2 value. This test is carried out with the supply off. The same test can be applied to all lighting circuits, whether they have two-way, two-in intermediate, or even just one-way switching. When using metal conduit as a CPC, parallel paths cannot be avoided, so we can make our link directly between the line and the earth terminal as shown in the video. The connection can be made between this point and the terminal bar, or between this point and the metal casing. This test can be carried out in the same manner as the lighting by testing between the line and the CPC at the circuit's extremity. A reading of 0.54 ohms can be recorded as the R1, R2 value. The same can be said for the SWA. Because the armour is being used as a CPC, parallel paths exist. So a link can be made here, and a test done at the extremity between the line and the CPC. So we remove the line, place a link on the line and a link onto the CPC. We could use the earth bar too. Then the test is done at the extremity, here at the isolator, between the CPC and the line as shown. This giving an R1, R2 value of 0.26 This test is carried out with the circuit dead or isolated. As this is an initial verification, no power will be on. But if it was an existing installation with power on, then this would have to be safely isolated. Please see the previous video on safe isolation. Ring final circuits are tested for continuity slightly differently. First, remove all conductors, the two lines, the two neutrals and the two CPCs. Then test the end-to-end values of each. Here we see the incoming and outgoing lines being tested. Here we see a reading of 0.69 ohms. Then the neutrals. Here we see a reading of 0.7, which is to be expected as they're the same size and same length. Then the CPCs, we see a reading of 1.1, which is again to be expected because the CPCs are 1.5, and therefore 1.67 times bigger resistance should be seen. Step 2 of the test requires connecting the outgoing neutral to the incoming line, the incoming neutral to the outgoing line by these links to form a figure of 8 position. Then we test at each particular socket between the line and neutral connections. This should be approximately the same as our predicted value, which is the line resistance R1 added to the neutral resistance Rn and divided by 4. Step 3 is the same, but this time we link the outgoing CPC to the incoming line and incoming CPC to the outgoing line. Again forming a figure of 8. I'm repeating exactly the same test, but this time between line and CPC at each socket. Again, this should be within our predicted value of the line resistance R1 added to the CPC resistance R2 and divided by 4. This test proves polarity, and the highest reading can be recorded as R1, R2. This test is carried out with the circuit dead or isolated. As this is an initial verification, no power will be on. But if it was an existing installation with power on, then this would have to be safely isolated. Please see the previous video on safe isolation. Electronic devices such as dimmer switches, RCBOs, can be damaged by carrying out the insulation resistance test between line to neutral. Care must be taken when carrying out this test on any installation. To carry out a global insulation resistance on initial verification, the power will be off, but all the protective devices and switches will be in the on position. Lamps and loads will be removed. So here we see the operator turning the switches on, checking that the lamps have been removed prior to carrying out the test. Any electronic devices like dimmers or RCBOs will be bypassed. Connect between the line and the neutral. Press our test button at 500 volts DC and toggle any two-way switches or two-way and intermediate switches to ensure that the test is done down all strappers. Repeat this test on line to CPC. This ensures all parts of the test have been carried out correctly. The only test left to do is between the neutral and the earth bar. A reading greater than 1 megohm is classed as satisfactory according to table 6.1 of BS 7671. Here we see the reading is greater than 299 megohms, therefore it is OK. When carrying out a global IR, a global insulation resistance test, if the reading is below 2 megohms, although this is classed as acceptable, it would mean that there is a possibility of a latent defect or latent fault. When this is the case, any reading below 2 megohms, each individual circuit must be tested, and then each individual circuit must comply with table 6.1 of BS 7671. To see how to carry out an individual insulation resistance, please see our other video. Testing the continuity of the protective conductors of the A3 radial socket circuit. We need to test that the earth is continuous throughout all the circuit from beginning to end. We take out the CPC and connect it to the line conductor. First remove the line conductor, then remove the CPC and connect them together using our test link as shown. Go to the furthest point and place our test socket. Null our instrument to make sure we have no resistance in the instrument. Here we see 0. Test between the line point and the CPC point. Switch the switch and press the test button, and we now have a resistance of 0.65. This is our R1, R2 test that we can record in our test sheets. Now, once the test is complete, we can reinstate the circuit, the line conductor back into the 20 amp breaker and the CPC back into terminal 1 of the earth bar. The equipment we need to test is as follows. We need a multifunction tester with varying scales from ohms, megohms, earth loop and RCD. We need test leads to GS38, crocodile clips, a test link or connector, a socket test point, and a selection of insulated screwdrivers. Testing the bonding conductors. First, we remove the main protective bonds that go to the incoming gas and the water. In this case it is just one bond, so we remove it from the earth bar to stop any parallel paths. Before testing, we need to null the instrument so that we get 0. Once this is done, we place one crocodile clip on the earth. The next we place on the pipe near the earth bond and test. Here we see that we've got an extremely low resistance, which we'd expect of 0. We repeat that with the water pipe and test. Again, we have an extremely low resistance of 0, which is to be expected. So we have proved continuity of the main protective bonds. This is a method 2 test. Once that is done, we place the bond back into our earth bar or earth terminal. Now we need to carry out our insulation resistance test on the A3 radial socket. This test is done by placing our instrument on megohms and testing between the line at the bottom of the breaker and the neutral bar first of all. Here we see a reading of greater than 299 megohms. We now can remove one of the conductors, the neutral bar, and place it on the earth bar and test between line and CPC. Here we see again greater than 299 megohms. Finally, we can take off our line conductor and test between the neutral bar and the CPC or earth bar. And again we see greater than 299 megohms. The minimum value according to table 61 in the regulations is 1 megohm.